All right, so we're going to do just some more examples from L'Hopital's rule and all these indeterminate forms, just to kind of make sure everybody's comfortable with them. And so this is where we left off on Friday with this 1 + 1 over x example and seeing how this exponential or this like function in the exponent changes our answer, right? And so just because we got 1 to the infinity doesn't mean it's going to equal 1 at the very end, right? And so here, let's just kind of continue with these. And so, example, let's look at the limit as x approaches infinity. Or no, yeah, nope. The limit as x approaches 0, I'm sorry. From the positive side of x to the power of x. And so here, when I try and just plug in 0, what is this going to equal? What is it going to give me? It wouldn't be 1 because, so it would be 0 to the power of 0, but that's not equal to 1. This is the only one where when you have a 0 in the exponent that it doesn't equal 1, right? And so that's why it's considered indeterminate. But yeah, I'm going to get 0 to the power of 0, and I can't really do anything with that. And so do you guys remember how to take care of this? What should I do to x to the power of x? How should I rewrite it? So if I kind of scroll back up here. Yeah, right. So change it so that I'm taking the logarithm of the first piece and then raising the whole thing to the exponential. And so here I'm going to have e to the x ln of x. If you're having trouble like memorizing that, because right on the exam, it's not like you get a cheat sheet or anything. You're going to have to know to do this whenever you have this indeterminate form. What you can kind of think of it as is, so here, I'm going to do some scratch work off on the side real quick. But so let y equal x to the power of x. And then you can take the logarithm of both sides. But then here, what you're doing is you can use this, I don't know if it's called the power rule for logarithms, but it's essentially the power rule, right? You bring that x down, but then you don't care about ln of y, you care about y. And so to undo that ln, you're going to just take the exponential of it, the e. And so that's kind of like the long version of what's happening here. Is everybody okay with that? Does that make sense? Does everybody see now why I'm writing it this way over here? Okay, nobody's saying no, so I'm gonna move on. But yeah, so here I want to find then the limit as x approaches 0 from the positive side. So this is why we needed that positive side, because I have ln of x right there, right? Oh, not x anymore. E to the x ln of x. And here, I want to say if you go back up to, this is the first example that we did, right? Down here. Oh, it's not the first one that we did, but we did this one. So I'll star this. And so we found, oh wait, what is it equal to? Okay, so we found that the answer was 0, right? And so here, I now just have that this is the limit. Oops. So remember, you can move that limit inside that exponential. And then now you're getting e to the power of 0. And so here, we found this limit above. And it's the one that I had starred. And so what is this equal to then? Yeah, this is 1. And so the limit as x approaches 0 from the positive side of x to the power of x is equal to 1. So any questions about that example? Okay, so then I'm going to start the next one. So I'm going to scroll up a little bit. And so here, let's look at the limit as x approaches infinity of x plus 1 over x plus 2, oh no, x minus 2 to the power of x. Here, when I plug this in, I'm going to get the power of, wait. When I plug this in, wouldn't I get x to the power of, or infinity to the power of infinity? But yeah, so here, this is one of those indeterminate forms with an exponent. And so what you're going to do is you're going to do the same thing that we've been doing. And so I'll do it the long way, just in case. But so I'm going to have x plus 1 over x minus 2 to the power of x. Wait, Matthew, what? Okay, so I'm going to get, yeah, and then I'm going to take the ln of both sides. So ln of y is equal to x, ln of all of that. And then I'll just take the e of both sides. Sorry guys. It's been doing this thing where it likes to kick me out for some reason. I don't know why. It's kind of annoying. I did it twice in my last class, so I apologize. I forgot to warn you that it might happen. But it looks like everybody's back, and it like keeps recording. I don't understand what's happening when it does this. But okay, any questions so far? Wait, what? Like, we don't need any of this? We need this. This is important. I'm not sure what you mean, Mohit. Okay, so let's finish this example. So really, when I find the limit as x approaches infinity, I know. That's what I mean, I was guessing. It's really hard to tell over like text, which is why this isn't the best way to teach, but it's okay. Okay, so here, what I really am finding the limit of is e x ln of all of this over x minus 2. But really all I care about is that limit of the exponent x ln x plus 1 over x minus 2. If I look at this limit here, this one right here, what is it equal to if I just try plugging in infinity? It would actually be, so here you would get infinity times ln of infinity over infinity. Okay, so I guess infinity over infinity here we're considering to be 1 for some reason. That's what I have in my notes. And so we're really getting infinity times 0. Oh, I know why. Okay, so here, all right, so real quick, let me kind of explain this. If I were to, so this is the indeterminate form 1 to the power of infinity. If you kind of think about this, regardless of the value of x that I plug in, those numbers are going to be really, really close, right? So if I let x equal like, so let's say x is equal to 1,000, then what you're getting is you're getting 1,001, oops, over 998, which is basically 1. And so the bigger that x gets, or even the smaller that x gets, the like closer to that value gets to 1, right? And so here, or I guess x is going to infinity, so we're not going to go to the negative side of it, but as x gets bigger, this is actually approaching 1. Does that make sense? Does everybody see why I have 1 right here? So let me kind of write that down. So as x goes to infinity, x plus 1 over x minus 2 approaches 1. Okay, there we go. So we're not actually getting infinity to infinity. It's 1 to the power of infinity, and that's why down here, right, we're getting 0 times infinity. Okay, so now that we've got that cleared up, this is another indeterminate form, no? And so I'm going to have to take care of that the same way that I took care of the x ln of x, right? And so here, I'm just going to focus on the limit, and I'll bring the e back in later because I just don't want to keep writing it. So x ln x plus 1 over x minus 2. What is the first step? So when I have the infinity times 0 indeterminate form, what do? I take one of my like functions, and what do I do with it? Yeah, you're gonna, instead of multiplying by it, you're gonna flip it and then divide by it, right? And so here, which one of these do you think is gonna be easier to like flip and then take the derivative of, right? So my options are ln x plus 1, x minus 2 over 1 over x, or the opposite of that, right? So which one of those should I use? The first or the second one? Oh man, it's got messy. Whoa, whoa. Yeah, the first one. And so here, I'm gonna have ln x plus 1, x minus 2 over, and I'll write it as x to the power of negative 1, just so it's a little bit easier. I'm gonna erase all of this. Then what can I do to the numerator of this to make it a little bit easier to work with? Because once I do L'Hopital's rule and get the derivatives, right? Because if I just try plugging this in, I'm gonna get 0 over 0, right? And so when I do this, what can I do to the ln that's up here? Do you guys remember those log rules I gave you before everything converted to online? I remember you guys did not remember them before I gave them to you. And so here, this is the one where you can take it and you can separate it as subtraction. Yeah. And so then on the bottom, and so it's just going to be easier to take the derivative of these two separate pieces, because once I take the derivative of this, I'm going to need the chain rule, right, to take the derivative of that. But to use the chain rule, I'm going to have to combine that with the quotient rule if I don't split it. And so splitting it just lets me have easier derivatives. And so don't forget about that. And so here, Now I'm going to do L'Hopital's rule. And so the derivative of ln is just 1 over whatever's in there. And then I take the derivative of what's inside, but what's the derivative of 1 plus x and the derivative of x minus 2? Yeah, it's just 1, so I don't have to change the numerator here. And so this is where I L'Hopital'd it. Okay, so if I try plugging this in now, oh, x to the negative 1, that's because really what I was doing was I took that x and I divided by 1 over x, right? And I just wrote this as x to the negative 1 instead of 1 over x, yeah. Okay, so, and then yeah, I took the derivative of that, so yeah. So here, when I try plugging in infinity, I'm gonna get 1 over infinity is 0 minus, so I'm still getting 0 over 0. And so rather than taking the derivative again, I'm gonna try and just simplify all of this using algebra, right? So what should I do to the numerator here? What should I do to both of these fractions? How do I actually subtract them though? Yeah, you need the common denominator, right? And so you're gonna have, so here I need to multiply this one by x plus 1 over x plus 1. And then I need to multiply this one by x minus 2 over x minus 2. And so I'm gonna get x minus 2 over x plus 1 times x minus 2 minus x plus 1. So here, let me rewrite this. And then that's still all over, oops, x to the negative x to the negative 2 power. And so here, actually, you know what? Here, if we write this as a fraction, if we actually write negative 1 over the x power of x squared, then I can just move this x squared up into the top here, right? So if I multiply this by negative x squared and then this by negative x squared. And so from here, it's just kind of algebra skills. There's not one way of getting this, right? There's a lot of different ways that you can simplify this to make it easier to look at. But so here, that's just going to cancel with that, and you get negative x squared times, oh yeah, this x cancels with that one. And so what do I have up here? Just negative 1? No, negative 3. And so what does this look like now? What am I going to have to do or use here? So if I actually FOIL this out, maybe it's easier to see that way. But so I'll have x squared minus 2x plus x, so minus x minus 2. So this is a limit as x is going to infinity of a rational function. And so when the degrees of these two things are equal, what is the limit equal to? Yeah, the ratio of those leading coefficients, right? So degree of f is equal to the degree of g. So the limit equals the ratio, oops, of the leading coefficients. And so here, the answer is just 3 over 1 And so the limit is equal to, oh wait, is the limit equal to 3? Yeah, it's e to the power of 3, right? Because all this was saying here was that the limit as x approaches the power of infinity of x ln x plus 1, oh shoot, x plus 1 over x minus 2, that's equal to 3. But the limit that we actually care about is not that one. We care about ln, oh no, x plus 1 over x minus 2 to the power of x. That's equal to the limit, or e to the limit x to the power of infinity, what we just found. And so this whole thing is e to the power of 3. So are there any questions about this example? It combined quite a few of the indeterminate forms, right? So at one point we had 1 to the power of infinity, and then at one point we had infinity times 0, and then eventually we had, it's either 0 over 0 or infinity over infinity. We had one of those, right? I forget which one. And so we saw 3 different types of indeterminate forms. So is everybody okay with all of this? I want to say this captured everything. Or except the infinity minus infinity one. All right, so I'll leave this up for a few, like maybe 30 more seconds. But if there aren't any questions about L'Hopital's rule, derivatives, anything related to like applications of derivatives, then we're going to start antiderivatives, which is the first step to integration. So are you done? Are you all done copying this down? Can you just type yes or no? I think that was everybody. I think Harshiel is the only one left to answer. Wait, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So nobody's saying no, so I'm just gonna start a new one. Okay, so here, this is section 4.8. And it's called antiderivatives. Actually, that's one word. And so let me tell you what an antiderivative is. Let me date these real quick. So this is the 23rd. So a function f, and here, whenever you kind of talk about antiderivatives, rather than using lowercase f, we're going to have capital F. So a function capital F is an antiderivative of little f on some interval, which I'm just going to use capital I to denote that interval for right now. So it's an antiderivative if the derivative of big F is equal to little f. for all values of x in that interval. So x in I. So let's do some examples. So let's find the antiderivatives. And so the first one we'll look at is little f is going to equal 4x cubed. And so I'm trying to find antiderivatives. So here we're looking for capital F. And so essentially, in words, if I were to kind of explain this, it would be you're working backwards, essentially, right? And so here, work backwards to find F, to find big F. And so you would essentially ask yourself, what would I take the derivative of to get little f? Right, so here, big F, so if little f is 4x cubed, what did I have to take the derivative of to get this as my derivative? Yeah, it had to be x to the fourth, right? Nothing else, when I take the derivative of it, is going to give me 4x cubed. And so here, it's x to the power of 4. Is everybody okay with that, with just the fact that antiderivatives, you're essentially just working backwards? Instead of finding the derivative, you're finding the thing that gave you that as its derivative. And so if we do another example, so if I give you that little f is equal to secant squared, secant squared of x, what did you have to take the derivative of to get secant squared? Yeah, it's tangent, right? And so here you can check your answers too. So if you take f prime or big F prime, you're gonna get secant squared of x, which is equal to little f, right? Same thing here if you do the check. And so if we do another one, so part C, if I give you that little h is equal to 1 plus 4 over 3x minus 1 over x squared, we can focus on each piece of this separately, right? So since it's addition and subtraction in the middle, I didn't have to use like the product rule or anything to get this. And so what did I take the derivative of to get 1? Yeah, just x. So that's that first piece, right? But then here, and then so remember constants or coefficients, they just kind of are along for the ride. And so that 4/3 was probably not really the result of taking the derivative, but it was probably just the result of having a 4/3 there in the first place, right? Because coefficients just go along for the ride. And so here, what I'm really looking at, and so I'll rewrite this real quick. This is 1 plus 4/3 times 1 over x. And so what did I take the derivative of to get that 1 over x? Yeah, that ln. And so here, when I look at big H again, this is now just 4/3 times the ln of x. Okay, and then if I look at x, or 1 over x squared. I can rewrite that as x to the power of -2. And so here, what did I have to take the derivative of to get that x to the -2 power? And so think of it this way. If I were taking the derivative of x to the -2, I would bring down that -2 and I'd have -3. And so here, taking the derivative, you subtract 1. And so if I wanted to go backwards, what am I actually doing instead? Yeah, you're gonna add 1. So what should my power be on x over here? So if I'm gonna have x, I should have the power of what? -1. But then here, should I have plus or minus before x to the -1? And think about what you have right here. Yeah, it's gonna be plus, because then when I bring down that -1, that's how I'll get this negative that's right in front of the x to the -2. And so, I'm gonna erase all that. Here, I can leave that part. And so this would be the antiderivative. And so let's check this one just because that's kind of long. And so here, capital H prime of x is going to be, if I take the derivative of x, I'll get 1. Here, I'm going to get 4/3 times 1 over x. And then here, when I take the derivative of x to the -1, I get minus x to the -2. And so this is the answer. Are there any questions about these antiderivatives? Or how I got any of these? Does this make sense? Okay, thank you, Matthew. I know I didn't really realize until I started talking through video that I ask a lot of questions and then like at once, and then a lot of the times you can answer yes or no to like the first one, but the second one has an opposite answer. And so yeah, I'm gonna try and stop doing that. It's the combination. Are there any questions? And then does this make sense? Right? You can't answer those with the same answer. But okay, so I'm gonna move on. Can anybody tell me what I can do to this capital H function and still, like, what can I add to this and still have it be an antiderivative of little h? Like, is this the only antiderivative? Yeah, I can add a constant, right? So note capital H of x equal to all of that, x plus 4/3 times ln of x plus x to the power of -1 plus 962. That's also an antiderivative. So is also an antiderivative of little h. And so that kind of brings us into our next theorem, right? And so here, I'll give you a theorem. If capital F is an antiderivative of little f on an interval capital I, then the most general antiderivative of f on I, is capital F of x plus some constant c. So where c is a constant. Have you guys seen this before? That plus C? Yeah, so if you've taken calculus before, which I think a few of you in the beginning said you had, then you'll know how important that plus C is. If you haven't seen it before, that's okay. I don't know if they're still up, but I want to say for a long time on almost every math room at Cal Poly, like math classroom at Cal Poly, the whiteboard or like the wall right next to the whiteboard would have a plus C written on it. I don't know if it's still there. You should, whenever school starts back up, you guys should look for them. But yeah, so basically that plus C, whenever you take and whenever you like integrate something, which we'll get to on Wednesday, but whenever you find an antiderivative or like a general antiderivative, you have to add plus C. You're not even going to use an actual number. It's literally the letter C, right? And so let's do some examples with this. So example, let's find general antiderivatives this time. And so the first one that we're going to look at is little f is going to equal 1 over the cube root of x. And so I'm going to start this problem the same way I started the first 3 examples I did for this section, right? I'm just going to find whatever function I took the derivative of to get this, but then I'm just going to add plus c at the end of it. And so here, what should I probably do to that cube root of x to make this a little bit easier to kind of think about, right? Yeah, write it as a power. And so I'm going to rewrite this as x to the power of negative 1 over 3. Yeah, make it a 1/3 power. And then I'm also going to make it negative just so that way I don't have a fraction to deal with. But then now I need to think about, okay, so what did I have to begin with to get this as my derivative? So what am I going to do to my power? I'm going to add what? Yeah, you're going to add 1, right? And so here, you're going to get that capital F of x is equal to x to the 2/3 power. Is it positive or negative? Oh, my answer key is wrong here. So let's check this. If I check this, do I get x to the power of negative 1/3 if I take the derivative of capital F like that? So here, if I leave it like this, then capital F prime, technically I would get 2/3 x to the negative 1/3 power, right? Which is not equal to what I have up there. So what am I missing from capital F? What do I need to multiply it by? Yeah, right. So to get rid of this 2/3 up right over here, I'm gonna have to, so here, let me, oops. Whoa, what happened? Okay, there it goes. So not equal. And so let me just change the color of this real quick. And so instead, you're gonna have that capital F is equal to 3/2 x to the 2/3. And so when I check now, you get 3/2 times 2/3 to the power of x to the negative 1/3, which does give you x to the negative 1/3. But what do I need to do to my final answer? plus c. Yep. And so there's the final answer here. That's the most general antiderivative that I could possibly find. So are there any questions about this one? Okay. So then in part B, we're going to look at little g is equal to cosine of 5x. And so I can't really rewrite this, but if I focus on just cosine, what would the antiderivative of cosine be? It would be sine, right? Because the derivative of sine is positive cosine. And so here, wait, is that right? Did I get that right? The derivative of sine is positive cosine and derivative of cosine is negative sine, right? That sounds right. Nobody's confirming or denying, so I'll believe that. And so here, okay, thank you, Jennifer. But so yeah, here, I know I'm gonna have in my capital G of x function, I know I'm gonna have a sine, and I know it's gonna have a 5x inside of it, right? Because when I take the chain rule, I leave the inside alone. So that means if I undo the chain rule, I'm gonna leave the inside alone again, right? But if I check this, so if I check it as it is right now, then the derivative of sine of 5x, so if I do the derivative, so I would get cosine of 5x, but then I would take the derivative of what's inside. And so what would I have, what would my coefficient be over here? Yeah, it would be 5. And so technically the derivative of sine of 5x would be 5 cosine of 5x. So if I want to get just cosine of 5x, what do I have to multiply g, capital G, by to get rid of that 5? Yeah, so I'm going to need a 1/5 out front here. Write that in black. Exactly. And so all I need to do to this is add my c, and I'm done. Are there any questions about this example? Okay. So then for part C, oops, sorry. For part C, what we're going to look at is little h is going to equal e to the power of 4x. So here, what is the antiderivative of e? Like, what did I have to differentiate to get e? Exactly, yeah, it had to be e, right? So the derivative of e is e, and the antiderivative of e is also e. So it's just this loop that it's always forever going in, right? And so here, I know my capital H is going to have an e in it. And what's the power going to be? Same kind of argument for why this right here, so like why the inside stayed the same right here. What should happen to my inside right here? What should it be? Yeah, 4x, right? Because if you take the derivative of e to the 4x, you get e to the 4x in there, right? And so here, if I check it just like this, so the derivative of e to the 4x, I would have e to the 4x, and then I would take the derivative of what's inside, and my inside piece here is that 4x. And so the same way I had 5 right here, I'm going to have a 4 right here. And so what am I going to have to multiply my capital H by to get rid of that 4? Yeah, that 1/4. And so my answer is capital H is equal to 1/4 e to the 4x plus c. Oops. Are there any questions about these examples? Okay. So I'm going to stop it here for now, and we'll continue this on Wednesday. There's a few more things to this section, but I kind of want to wait to start that when we start integration on Wednesday. And so I'm going to open up this homework. You're going to be able to do most of it. But I'm also going to stop the lecture, or like not the lecture, the recording.